Welcome to lesson 34 in power system analysis. In this lesson, we will continue with our discussion on power system stability. We will start with the swing equation which we had developed in the last lesson, and we will see how we can include the damping term in the swing equation. Then we will discuss about the most important stability analysis model, which is the single machine connected to infinite bus system. We will see how we can convert a two machine system or even a multi machine system into this kind of a model for stability analysis, and then we will take up a few examples to show how we can apply these concepts to power systems. Well, on completion of this lesson, you should be able to develop the dynamic equation of motion for synchronous machines, which you have already done in the last lesson, but what we will do is we will extend this to include the damping terms. Next, you will be able to develop the mathematical model for stability analysis of single machine connected to infinite bus system. That is what we will do more in detail in this lesson, and we will also see how we can convert different kinds of systems into this kind of a model. So, let us start with the swing equation that we had developed in the previous lesson. We will go about it a little quickly. Well, we had said that if we have a system where we have a generator and which is supplying electrical power output to some loads, this generator to supply this electrical power output is run by means of a prime mover. This prime mover power, that is the turbine power, is the mechanical input Pm, and this mechanical input is driving this rotor of the turbine and the generator, and this causes a torque on the turbine shaft or the rotor shaft of the generator turbine. This torque we call as Tm, and since there is an electrical power output from the generator, this electrical power is going to also exert a torque on the rotor of the synchronous machine. This torque will be opposing the mechanical input torque. So, this we have shown as T in the opposite direction. When these two torques are equal or balanced, then we get a constant speed, which is the synchronous speed of the machine. So, we get omega s, which will be a constant if Tm and T are equal. The same situation holds good in case of a motoring machine, that is when we have a synchronous motor. Only thing is, here the electrical power will be an input and the mechanical power will be an output. So, the same relationship will hold, except that both the electrical and mechanical power in this case will have to be taken as negative of what we have taken in case of generator system. So, for generator system, we consider this Pm and Pe as positive. Similarly, this Tm in this direction and T in this direction, we consider T in this direction, we consider them as positive, whereas in case of motor they all will be having negative sign. So, going back here, whenever there is a difference in these two torques, that is the torque Tm and Te, if Tm is more than Te, then what is going to happen is this rotor shaft is going to accelerate, and that is there is going to be an acceleration of this rotor shaft, and this acceleration will be given by this relationship, this relationship J d2 theta m by dt2, where d2 theta m by dt2 is basically the acceleration that we have. Theta m is the rotor position with respect to a stationary reference frame, and Tm of course is the mechanical torque input, T is the electrical torque which is the output. So, Tm minus T, all these are in Newton meters. So, theta m, as we said, is the rotor position which is in mechanical radians. Tm is the turbine torque in Newton meter, and as we said, in case of motoring machine, since this will be an output, so this will have a negative value. Similarly, T is the electromagnetic torque developed in Newton meter. This is the electrical, since electrical power is an output. So, the torque developed is the electromagnetic torque, and this is in Newton meter. If we have the synchronous motor, then this will be negative value. So, this all we had already discussed in the last lesson. Now, instead of working with torque, we normally work with power. So, what we do is we multiply this relationship with the mechanical speed in radians per meter, then we get j omega sm, where this is the mechanical speed of the rotor, s is denoting synchronous speed. So, since rotor will be rotating very near to the synchronous speed, that is at the time when we are talking of this acceleration taking place. So, we write j omega sm into d2 theta m by dt2 into 10 to the power minus 6 we have taken, because we want to write this expression in terms of megawatts into. So, into 10 to the power 6 is equal to P m minus P into megawatt. Sorry, I think this should be 10 to the power minus 6. Okay. So, this should be 10 to the power minus 6, because we want to write this in megawatt. If we do not multiply this, then this will be in terms of watts. So, j omega sm d2 theta m by dt2 into 10 to the power minus 6 is equal to P m minus P e in megawatts, where P m is the mechanical power input and P e is the electrical power output. All these are in megawatt. What we have done in this case, that we have assumed that there is no losses taking place in the electrical machine, that is P m minus P e for a synchronously rotating rotor will be 0. There is no loss which is taking place. One can always take care of losses if one wants by modifying P m or P e to take care of them. Now, instead of working with the mechanical speed, we normally work with the electrical speed, and we had already seen the relationship between the electrical speed and the mechanical speed, or the electrical angles and the mechanical angle. This relationship is the electrical quantities are equal to P by 2 times the mechanical quantities in terms of speed or in terms of angle. So, what we will get is, since we have omega sm which we want to write as omega s, then omega sm will be equal to 2 by P into omega s, because omega s is equal to P by 2 omega sm. So, we get 2 by P here. Similarly, here we have the theta m in the earlier expression, that is, this was theta m, and we want to write it in terms of electrical angle, so, or electrical position of the rotor. So, we will get again 2 by P into theta e here. So, this 2 by P is again taken here. So, it becomes 2 by P square. So, j into 2 by P square omega s into 10 to the power minus 6 d2 theta e by dt2 is equal to P m minus P e megawatt, okay, where theta is the angle in electrical radians. Now, this term in bracket, as we have shown earlier, is what we call the angular momentum of the rotating mass, which is the rotor of the turbine and the generator system. So, this we write as m. So, we get m d2 theta e by dt2 is equal to P m minus P e. Now, what we normally do is, because this theta e will keep changing with time, that is with every rotation theta e goes, that is every one cycle of electrical rotation, this theta e changes by 360 degrees electrical, and therefore, it will keep on changing with time. So, instead of working with this theta e, which is with reference to a stationary reference frame, we work normally with a rotating reference frame, which is rotating at synchronous speed. So, with respect to a synchronously rotating reference frame, this value of theta will be much smaller, and it will not keep changing unless there is a change in the speed of the rotor from the synchronous speed. So, as I said, it is more convenient to measure the angle or the position, angular position of the rotor with respect to a synchronously rotating reference frame. So, if we do that, that is, we write that angular position as delta, then delta will be equal to theta e minus omega s into t. At synchronous speed, of course, theta e will be equal to omega s into t plus the angle which is going to be its reference. So, we have delta is equal to theta e, because this theta e every cycle is equal to omega s for into time for one cycle. So, we subtract this, then we get the angular position with respect to the rotating reference frame. So, delta is equal to theta e minus omega s into t, rotor angular displacement from synchronously rotating reference frame. So, delta is this rotor angle displacement from synchronously rotating reference frame. This delta is generally called as the torque angle or the power angle. Now, in this relationship, we want to replace this theta e with delta. So, we need to find out the value of d2 theta e by dt2 in terms of delta. So, what we do is we take this omega st on the other side and differentiate it once, then we will get d theta e by dt. So, d theta e by dt will be equal to d delta by dt plus this omega s into t was on this side. So, this was plus omega s t, and once when we differentiate it with respect to t, we will get omega s here. So, d delta by dt plus omega s, differentiating it again, we will get d2 theta e by dt2 is equal to d2 delta by dt2. Here omega s is a constant. So, this differentiation will be 0. So, we get d2 theta e by dt2 is equal to d2 delta by dt2, and therefore, this relationship which we had in terms of the electrical angle with respect to our stationary reference frame can be now written in terms of rotating reference frame or in terms of power angle as m d2 delta by dt2 is equal to P m minus P e. And many times, since we have said from the very beginning that we work mostly with the per unit system, therefore, dividing this expression by the rating MVA rating of the machine, we will get the per equation in per unit. So, we will get m per unit into d2 delta by dt2 is equal to P m minus P e, where the power P m and P e are also in per unit instead of in megawatts. Here m per unit, as we had seen earlier, we had written that kinetic energy is equal to G into H, where G is the rating of the machine and H is the inertia constant, or we had defined the inertia constant H as the kinetic energy of the rotor at synchronous speed divided by the rating of the machine in MVA, whereas kinetic energy we have taken in terms of megajoules. So, using that relationship, we had shown in the last lesson that m is equal to h by pi f. So, replacing this m by this value h by pi f, we can write this expression as h by pi f d2 delta by dt2 is equal to Pm minus Pe in per unit. This equation we call as the swing equation of the synchronous machine. Now, in this whole expression, we have not considered the damping torque at all. The mechanical torque input and the electrical output torque were considered, whereas we did not consider the damping torque, but whenever there is going to be a relative motion between the synchronously rotating magnetic field in the air gap and the rotor positions or the rotor speed, then there is going to be a voltage developed in the rotor bars, and since these damper bars placed on the rotor, and since these damper bars are short circuited, there is going to be a current which will flow in these damper bars. This interaction of this current with the field will produce a torque which is going to oppose the motion. So, whenever there is a relative motion, this motion is going to be opposed by the damping torque. So, damping torque will always be opposing the relative motion. So, damping torque produced by the damper winding, as we said, is proportional to the slip speed, because now this damping torque is produced only when there is a relative motion. Whenever there is a relative motion, depending on this relative motion, only the voltage gets produced. So, the voltage is going to be proportional to this relative motion, and since the bars will have a constant resistance, so the current will also be proportional to this relative motion, and thereby the torque produced is also going to be proportional to this relative motion, which we call as the slip speed. So, the damping torque is proportional to the slip speed, the speed difference from the synchronous speed and the actual speed of the rotor. Therefore, we are writing damping torque T d as proportional to omega e minus omega s, where omega e is the actual rotor speed in electrical radians per second, omega s is the synchronous speed of the rotor in electrical radians per second. So, T d is proportional to omega e minus omega s, and we have omega e minus omega s can be written as omega e is nothing but d theta e by dt, that is with respect to the stationary reference frame, the angular position, the derivative of the angular position will give us the speed of the rotor in terms of electrical radians per second. So, we are writing this as omega e is d theta e by dt, and omega s of course is the synchronous speed. So, this we can write now theta e we can write as omega s t plus delta, as we had seen earlier when we defined the synchronously rotating reference frame. Theta is equal to omega s t plus delta from here. So, we are simply substituting this value here. So, d by dt omega s t plus delta minus omega s. So, this comes out to be d delta by dt as the differential of derivative of d omega s t with respect to time t is equal to omega s, which will cancel with this omega s. So, we have got d delta by dt. Now, the damping power P d will be equal to T d into omega e, right, and T d we are saying is proportional to omega e minus omega s. So, we can write this as k times omega e minus omega s into omega e. This omega e is given here. So, P d is equal to k omega e minus omega s into omega e. This is equal to k times omega s plus d delta by dt minus omega s, that is from here we are writing this. So, actually we can write this omega e as that. So, omega e is omega s plus d delta by dt minus omega s into this omega e, again we can write this as omega s plus d delta by dt. So, we have got this relationship now, P d is equal to k omega s plus d delta by dt minus omega s into omega s plus d delta by dt. This omega s will cancel out. So, we have got this relationship now as k into omega s into d delta by dt, that is d delta by dt we multiply with this omega s. So, we get omega s d delta by dt, this d delta by dt we multiply with this d delta by dt. So, we get d delta by dt whole square. So, we get this as k omega s d delta by dt plus k d delta by dt whole square. Now, d delta by dt will be generally small, the change in the rotor speed from synchronous speed is not very large. Therefore, this term d delta by dt whole square is going to be very small and we can neglect it. So, we can write this as k omega s d delta by dt approximately equal to that, and this we generally write as d into d delta by dt, where d is called the damping coefficient of the synchronous machine. So, with this P d is equal to d delta by dt, we can now put this damping power in the swing equation of the synchronous machine. In that case, we will get this as h by pi f d 2 delta by dt 2 plus d delta by dt is equal to P m minus P e. That is the expression that we will get. In this case, we have not included one more damping term which comes because of the friction, that is there is a friction power or damping power due to friction is also there. Normally this power is much smaller and this is more or less constant, and this is normally taken care of by subtracting it from the mechanical input itself. So, when we talk about the mechanical input, we are talking about the net mechanical input, which has already taken care of the frictional losses or the frictional power loss which takes place in the machine. So, this is already taken care of, and therefore, with the damping the swing equation now we have is like this. Now, we will take one small example to show how we can write the swing equation for a synchronous machine. So, let us take this example. We have a 50 hertz 20 pole hydroelectric generator rated at 500 MVA, 20 kV, and has H is equal to 2 megajoules per MVA. Now, here we are seeing a synchronous machine with 20 poles. Now, normally with hydroelectric generators, the speed is much lower compared to that of a thermal generator or turbo generator, where the steam turbine work at high efficiency at high speeds, and normally the speed for these generators will be of the order of 3000 rpm. So, we need only 2 poles for these machines, whereas for hydroelectric generators the speed depends to some extent on the type of the turbine we have as well as on the head available, that is the height of the water which is available, and these speeds are generally much lower. And just so, in order to generate power at 50 hertz, we need much larger number of poles. That is, when we have 20 poles on the system, the speed is going to be much, that is at much lower speed we will be able to generate power at 50 hertz. So, determine its omega s, that is what is the synchronous speed of this machine, and what is the synchronous speed in mechanical radians per second as well as in electrical radians per second. Second part is write the swing equation for this generator. So, we need to write down the swing equation. The third part is the generator is initially working at Pm is equal to Pe is equal to 1 per unit with delta is equal to 10 degrees. That is, initially the delta angle or the power angle is 10 degrees. When a 3-phase short circuit occurs at its terminals, which results in its electrical output reducing to 0 for t greater than 0. That is, at t is equal to 0 plus we are assuming a 3-phase short circuit occurs at the terminals of the machine. Since a 3-phase short circuit has occurred on the terminals of the machine, the voltage goes to 0 and thereby there is no electrical power output from the generator. So, at t is equal to 0, the electrical output at 0 plus electrical output becomes 0 for all t greater than 0. Determine its power angle delta 3 cycles after the short circuit. That is, after the short circuit, after 3 cycles, what is going to be the angle delta? Actually, what happens? We have the mechanical input to the machine before the fault was equal to 1 per unit, which was same as the electrical output. So, Pm minus Pe was in that case 0 and the speed of the machine was synchronous speed and the delta angle was constant. Whereas, when at t is equal to 0 the fault occurs, the Pm remains same because the mechanical input to the generator changes much slowly, whereas the electrical output from the machine at t is equal to 0 plus has reduced to 0. So, Pm minus Pe now is equal to 1 per unit and this is going to cause an acceleration of the rotor of the turbine generator system. And because of this acceleration of the rotor, the delta angle or the power angle of the machine is going to change and we are asked to find out this power angle after 3 cycles. So, this says determine its power angle delta 3 cycles after the short circuit, assume the mechanical input power Pm remains constant at 1 per unit during this time. This is what we said. Normally, the power input, mechanical power input, it does not change in this short period and therefore, we are assuming it to remain constant at 1 per unit. Now, for the first part, we know that the frequency is 50 hertz. So, the speed of the synchronous speed of the generator omega s will be equal to twice pi f, which is equal to 314 radians per second. So, twice pi 2 pi into f, f is 50 hertz. So, this comes out to be 314 radians per second. Now, omega s m, the mechanical speed, is given by 2 by p into omega s. Now, in this case we have p is equal to 20. So, we have 2 by 20 into omega s 314 radians per second. So, this speed comes out to be 13.4 radians per second. So, we see that the speed of this generator will be in terms of RPM will come out to be 300 RPM, whereas in case of for a 2-pole generator if we were running, then the speed would have been 3000 RPM. So, for a 20-pole generator the speed is 31.4 radians per second and we can convert it in RPM, then we will find that this comes out to be around 300 RPM. Second part is we need to write down the swing equation for this machine. Swing equation, as we have seen earlier, we write down as h by pi f into d2 delta by dt2 is equal to Pm minus Pe in per unit. Now, here the h of the machine has been given as 2 and f is 50. So, we simply write 2 by pi 50 d2 delta by dt2 is equal to Pm minus Pe. This is the swing equation for this machine. So, we can write down the swing equation for any machine knowing its inertia constant and the frequency and if we know these powers, then this is P m is equal to 1 and P whatever is the output. If there is a difference, we are going to get an acceleration. If these two are equal, the acceleration will be 0, the speed will remain constant. Now, the third part is we have been told that initial power angle delta 0 is 10 degrees, which is equal to 0.1745 radians. Also at start t is equal to 0 plus d delta by dt is equal to 0, that is just after the fault has occurred, the speed cannot change much. So, the speed at t is equal to 0 plus is 0 only, that is d delta by dt is 0, the change in speed from the synchronous speed is going to be 0. So, d delta by dt is equal to 0. Now, P m 0 plus is equal to 1, that is we have assumed that the mechanical power input has not changed after the fault for the time under consideration, and P e 0 plus is equal to 0.0 since the fault has occurred. So, after the fault we have immediately after the fault we have this power output as 0. Therefore, now substituting these values in the swing equation, we will get 2 by pi 50 into d2 delta by dt2 is equal to P m is 1 and P e is 0. Now, this is the swing equation which is valid for this operating condition. Now, integrating this once, we will get d delta by dt is equal to twice pi into 50 by 4 into t plus 0. That is, we are writing instead of pi into 50, we are multiplying it by 2 on numerator and denominator. So, twice pi into 50 and this becomes 2 into 2 4, and when we take this on this side, then we have d2 delta by dt2 is equal to 2 pi 50 by 4 into 1. Now, integrating this, we will get d delta by dt is equal to 2 pi 50 by 4 into t plus 0, because we will get plus d delta by dt at 0 plus we have seen as 0. So, the constant of integration here is 0. Now, integrating again, we will get d delta with respect to time, this is a function of time, is equal to twice pi into 50 by 8. We are integrating this t, so we will get t square by 2. So, just substituting that, we will get twice pi 50 by 8 t square plus the constant of integration, and we have seen delta 0 is equal to 0.1745 radians per second, sorry 1.1745 radians. So, we are substituting that value here and we get d delta at any time t from this expression. Now, we have said t is we want to find out the delta after 3 cycles. So, t is equal to 3 cycles, and at 50 hertz this comes out to be 60 millisecond. Therefore, that is 0.06 second. So, substituting for t, delta at 0.06 second is equal to twice pi into 50 by 8 into t square, that is 0.06 square, plus delta 0, which is equal to 0.1745, and when we do this, we get this value as 0.3158 radians, which is equal to 18.1 degrees. That is, in just 60 milliseconds, we have seen the rotor angle has changed from 10 degrees to 18.1 degrees. So, this is how we can try and find out the rotor angle by solving the swing equation for the given machine. Next, we will try to see how we apply this to for stability analysis of different systems. Now, here we will start with first using the synchronous machine electrical model. Now, here we have already seen earlier that simplified model for the electrical machine can be seen as a voltage source in series with a reactance, which is the direct axis reactance when we are talking about the cylindrical rotor machine. then we have the internal voltage E dash is equal to V plus J x d dash into I. Normally, when we are working for stability analysis, since we are talking in terms of transient small periods in which we are talking about the dynamics of the rotor of the machine. So, we are using the transient reactance of the machine. So, this is what we will get in case of a cylindrical rotor machine, but if we are using a salient pole machine model, then the internal voltage E dash will be given by V plus R into I. I have used the resistance also. Normally, this resistance is negligible and one can neglect this term R into I. Otherwise, if we want to use it, then this can be used. So, V plus R I plus J times x d dash into I d plus J times x q dash into I q. This is the expression which will give the internal voltage of the machine, and that is the internal voltage E dash will have a magnitude E dash and an angle delta, and this internal voltage with its reactance as shown for the salient pole machine or for the cylindrical rotor machine will give us the machine model. Now, we will go into the most commonly used model for transient stability analysis. As we had said earlier, when we talked about the definition of the stability, that many times we are interested in studying the stability of a single machine or a group of machines, not all the machines in the system or the complete system as such. So, this is one model which is very used in power system stability analysis, which we call a single machine connected to infinite bus system. Actually, what we can see this as, if we have connected any machine to a very large system, then this system being very large, this will have very large inertia, and any change in power in this is hardly going to affect the speed or the frequency of the system. Also, since this system is very large and it has very large number of generators, the reactive power reserve will also be large enough. So, any changes in reactive power flow from this is not going to change the voltage magnitude of this bus. That is, in terms of active power as well as reactive power, the changes caused by this machine are too small to create any changes in the behavior of this machine, and that is behavior of this system, and that is why we call this system as an infinite bus. That is, we say this machine is connected to an infinite bus, the voltage of which we write normally as V infinity, and since the rotor angle for this system is not going to change with the power flow from this machine, we normally use this voltage angle or the power angle of this bus, where which this system is connected to the where this machine is connected to the system, as the reference voltage V, which we put as 0 degrees. So, the voltage at this bus V infinity is not going to change, it remains constant or invariable with any change which takes place with this machine, as well as its angle does not change, and therefore, we can think of this infinite bus as a ideal voltage source for complex voltage. That is, it is a ideal voltage source whose voltage magnitude as well as angle do not change at all. So, in terms of circuit analysis, we had talked about ideal voltage source where the voltage does not change whatever may be the power which we draw from it. Similarly, the voltage of this bus is not going to change, that is, the complex voltage of this bus is not going to change whatever may be the power drawn or supplied from this bus. So, we can think of this system which we call as the infinite bus as an ideal voltage source for complex voltage. So, if we look at that, then we can see here this machine is connected to this infinite bus or this large system by means of an external reactance. This reactance will normally be the reactance of the transformer and the transmission line through which this generator gets connected to the system, which we write as Xe, and X dash D is the reactance of this machine, that is direct access transient reactance of this machine. Here I had shown this is the ith machine. Similarly, we can think of all different machines, and when we are trying to study the stability of any single machine, this can be any machine, one machine in the system. Okay. So, this is how this model is prepared, and the electrical model of this can be given as the machine internal voltage E dash angle delta, X d dash is the direct axis reactance of the machine, and X e the external reactance, which is the reactance of the transformer or the transmission line. This is connected to an infinite bus whose voltage is V infinity and angle is 0 degree, and this machine is supplying a power to the system or the infinite bus, and this power is P e. So, this is the system that we call as the single machine connected to infinite bus system, and as we had seen in case of the synchronous machine analysis, the power delivered by this machine to the infinite bus is given by this relationship P is equal to E dash V infinity by X t, where X t is the transfer reactance. It is the total reactance between the internal voltage of the machine up to the infinite bus. So, X t sin delta plus V infinity square by 2 into 1 by X d X q dash minus 1 by X d dash. These hats are taken to take care of the total reactance in the direct axis and the quadrature axis as such. That is, we define X t as X d dash plus X e, and X d hat X d dash hat is equal to the same reactance, that is X t, and X q dash hat is X q dash plus X c. That is, what we have done is we have included the external reactance along with the direct and transient and the quadrature axis reactances of the machine. Normally, if we are considering a cylindrical rotor machine, which we do most of the time, then of course X d dash and X q dash will be equal, and therefore, this second term vanishes, that is, it goes to 0. This minus this is, since these two terms are same, so this will be 0, and we get the relationship which is P is equal to E dash into V infinity by X t into sin delta. This is the relation which we had seen a number of times. We write this E dash V infinity by X t as P max. So, we get P is equal to P max sin delta, that is, the electrical power output from the machine to the infinite bus is dependent on the power angle delta of the machine. That is, it depends on by how much this angle delta is leading the voltage angle at the infinite bus. If it leads this, then the power is being transferred from the synchronous machine to the infinite bus. If it lags, then the power will be transferred from the infinite bus towards the machine, that is, it will start acting as a motor. Okay. So, now since we know that the electrical power output is given by this relationship, so we can replace this relationship into the swing equation of the machine. So, we can write this swing equation for this machine now as h by pi f d2 delta by dt2 plus d by d delta by dt is equal to P m minus P e. Instead of P e, we are now writing this as P max sine delta. This is a second order nonlinear differential equation, nonlinearity cropping up because of this trigonometric function here, and this is a second order differential equation. So, we need to solve this second order nonlinear differential equation for this simplified single machine infinite bus system when we want to study the stability of the system. Now, let us see how we can convert different systems into a single machine infinite bus kind of a model. Let us take the situation where we have two machines, two synchronous machines connected to each other. We have xd1 dash as the direct axis transient reactance of machine 1, xd2 dash as the direct axis transient reactance of machine 2, xc is the reactance by which these two machines are connected to each other. It is the reactance of the line which connects these two machines. Now, certainly when we have connected these two synchronous machines, one will be acting as a generator, another will be acting as a motor. So, machine 1 acting as a generator, we have mechanical power input and electrical power output. This machine internal voltage we are writing as E 1 dash with an angle delta 1. The machine 2 is acting as a motor. So, electrical power is input to this and mechanical power is output to this. So, and its internal angle we are writing as E 2 dash with an angle delta 2. Now, since we have assumed there is no losses taking place in the system, so we will have P E 1 is equal to P E 2 and similarly P m 1 is equal to P m 2. So, we are writing P m 1 is equal to minus P m 2 because in the case of the motoring machine, machine 2, since it is motoring and the mechanical power is an output. So, we are writing this negative for that. So, P m 1 is equal to minus P m 2 which we write as P m. Similarly, P E 1 is equal to minus P E 2 because in case of machine 2 the electrical power is an input not an output. So, this negative sign is to take care of that. So, P E 1 minus P E 2 is equal to P E, and now substituting this expression for the swing equation, we will have d 2 delta 1 by dt 2 is equal to pi f by h 1 into P m 1 minus P E 1. So, we can write now this P m 1 minus P E 1 as P m minus P E from here P m 1 P E 1. So, P m 1 is P E P m and P E 1 is P E. So, we are writing pi f P m minus P E by h 1. Similarly, for the second machine we will have d 2 delta 2 by dt 2 is equal to pi f by h 2 into P m 2 minus P E 2, and since we have P m 2 minus P m 2 as P m and minus P E 2 as P E. So, this will become positive P E and this will become negative P m. So, we have got pi f by h 2 P E minus P m. Now, subtracting these two equations we will get, that is if we subtract these two equations, that is equation 2 from equation 1, we will get d 2 delta 1 minus delta 2 by dt 2 is equal to pi f h 1 plus h 2 divided by h 1 h 2 into P m minus P E, and this we can write as, if we take this term on this side as h equivalent by pi f d 2 delta by dt 2 is equal to P m minus P E in the same form as the equation we had for a single machine connected to infinite bus, except that in this case the h equivalent we are writing and the angle delta we are writing, which is delta 1 minus delta 2. After all, we have seen it is, we have used the reference angle as 0, which was the angle voltage angle of the infinite bus. So, if we take delta 2 as the reference angle here in this case, then we have delta 1 or the delta 1 minus delta 2 is basically the difference in the angle of the two machines. So, this turns out to be an equation which we are using for a single machine infinite bus system. So, the swing equation which describes the motion of this two machine system can be written in this form, where we have H E q as the equivalent inertia and delta, which is delta 1 minus delta 2, is the angular difference of the internal voltages. And H E q we have got as H 1 H 2 by H 1 plus H 2, and the electrical power transfer in this case will be given by, we had E v by x t. So, here E is the machine 1 internal voltage E 1 dash, and V is the second machine internal voltage, that is E 2 dash, divided by x t, which is x d 1 dash plus x e plus x d 2 dash into sine delta. We have seen how we can convert a two machine system into a single machine system. However, this kind of a conversion to a single machine infinite bus system is not possible for a large multi machine system. In this case, we need to write down the swing equation for each machine separately and solve the swing equation for all the machines to look at the dynamics of the system. Now, when we see this multi machine system, we have to understand one thing, that the machines have different ratings and their inertia constants are normally provided in terms of the machine rating or machine base itself. So, for a machine I in the system, if the rating is given as G machine I, which is the base value, these values will be different for different machines in the system, because in a large system we have large number of different ratings of machines. So, we need to choose a single system MVA base for a multi machine system. So, let us say that we have chosen G system as the system base for this multi machine system. Now, what we have to do is we have to convert the inertia constants of all the machines like this. For machine I, H machine I has to be converted to the system base, and this we can do by multiplying H machine I by G machine I divided by G system, because when we multiply by G machine I, we get the kinetic energy of the machine rotating part, and we divide it by G system, then this becomes the inertia constant for that machine in terms of the system base, because we define H as the kinetic energy of the machine divided by the rating or the MVA base of the system. So, this is how we can convert it. So, we write the swing equation now in this form: G machine I by G system is equal to H machine I by pi f into d 2 delta I by dt 2. This is equal to P m I minus P E I. Now, these ratings also initially would be given in terms of machine ratings. So, here also we convert them to the system base. So, in terms of system base in per unit values. So, we multiply it by G machine I, then it converts into mega MVA, and we divide it by system base. So, then this becomes converted to the system base in per unit. So, this is what will result when we write this in on system base. H system by pi f into d 2 delta I by dt 2 is equal to P m I minus P E I in per unit on the system base, where H system, as we have seen, is equal to H machine I is into G machine I by G system, that is the inertia constant of machine I on a system base is given by this. Now, when we have a number of machines connected to the system, we will find that some machines are swinging together, whereas some other machines may not be or may be having a different swing from each other, especially if we have a number of machines at a particular generating station. This is going to happen, that is, all those machines will be experiencing the same amount of disturbance, and therefore, they will be swinging together. these machines which swing together, we call them as coherent machines. So, for coherent machines, we can write the swing equations and combine them and make an equivalent single machine equation for them. So, consider the swing equation of two machines on a common system base. So, we have H 1 by pi f d2 delta 1 by dt 2 is equal to P m 1 minus P e 1. This is for machine 1. Similarly, on the same system base, we have H 2 by pi f d2 delta 2 by dt 2 is equal to P m 2 minus P e 2. Now, if the machines are swinging together, then delta 1 and delta 2 will be same, that is the relative motion of these two machines are same. So, delta 1 is equal to delta 2 is equal to delta, and therefore, adding these two equations, we can add them. If we add them, then we will get the equation in terms of H equivalent by pi f d2 delta by dt 2 is equal to P m minus P e, where P m is equal to P m 1 plus P m 2, P e is equal to P e 1 plus P e 2, and H equivalent is equal to H 1 plus H 2. So, this way what we have seen is that the coherent machines, their inertia can simply be added together, and we can make a single machine equivalent for the coherent machines. Now, let us take a very small example here. A power plant has two 3-phase 50 hertz generators with following ratings. Generator 1 500 MVA 20 kV 20 poles, H is equal to 3 seconds. Generator 2 200 MVA 15 kV 2 poles, H is equal to 6 seconds. Write the swing equation for each machine on a system base of 100 MVA. If the machines are assumed to be swinging together, that is they are coherent, write the swing equation for the equivalent machine. The swing equation for each machine has to be written on a system base of 100 MVA. So, first we will convert the inertia of each machine to a 100 MVA base. So, H 1 nu, which is the inertia of the machine 1 at 100 MVA base, will be H 1 old into S 1 old divided by S 1 nu, which is same as G old by G nu. So, 3 into 500, which was the machine base for this, 3 into 500, and this is the system base. So, 3 into 500 by 100, which is 15 seconds. Similarly, for the second one, we will get this as 6 into machine rating 200, and this is the system base. So, this comes out to be 12 seconds, and therefore, putting the value of H on the system base of 100 MVA, we get the swing equation as H we have written here for machine 1, H for machine 2 as this. So, 15 by pi f d2 delta 1 by dt 2 is equal to P m 1 minus P 1, and for second machine 12 by pi f d2 delta 2 by dt 2 is equal to P m 2 minus P e 2. Now, if the machines are coherent, then we are saying delta t is equal to delta 1 t is equal to delta 2 t. In that case, what we have seen is the mechanical powers will also add up, the electrical powers will add up, and the inertia also adds up. So, we will add up the inertia and we will write 27 by pi f, that is 15 plus 12. We have got this 15 and this 12. So, inertia gets added on the same base, both are there. So, 27 by pi f d2 delta by dt 2 is equal to P m t minus P e t, where P m is equal to P m 1 plus P m 2 and P e is equal to P e 1 plus P e 2. So, in this way we can write the swing equation for coherent machines. So, with this we will stop today. In the next lesson we are going to talk about small signal stability analysis for this rotor angle deviations. So, small signal stability analysis